Hello everyone, welcome to my presentation today. It's going to be related to HAPS, High Altitude Platform Stations, which is an important point and hot topic in wireless communication these days. So I will be talking about that and discussing NTN in general and HAPS in specific. My name is Metin Öztürk. I'm from Ankara, Yıldırım, Beyazıt University. I'm also a director of Redefining Non-Terrestrial Networks lab. So first, I'm going to start with a brief background, personal background. So this is my family. So I was born in Eskişehir, specifically in Odunpazarı, and also I got my PhD and my undergrad and master degree from Electrical and Electronics Engineering. Then I moved to UK, Glasgow, University of Glasgow to do my PhD. I did my PhD there at James Watt School of Engineering. Then I worked as a project researcher, part-time researcher at University of Jyväskylä in Finland, and also research project assistant at Ajman University in United Arab Emirates. And recently I was a visiting professor at Carleton University, Canada. In IBU, in Department of Electrical and Electronics Engineering, I have a quite track record of history. I was a research assistant between 2016 and 2020 and a lecturer between 2020 and 2021. Then since 2021, I'm working as an assistant professor there. Then I'm married and have one kid. So let's have a look at the evolution of mobile communication first. So then this is going to be a foundation of the discussion with non-terrestrial network. So actually the story started from 1980s, where we had like 1G, but for sure at that time we didn't call it 1G. It was just a mobile communication. So it was very primitive, just analog communication was available, then just voice-based communication. Roaming was not available, and it was quite primitive, but it was just the start of the storyline. Then when we came to 1990s, we met 2G, basically, aka GSM. So then GSM was quite successful today. Even today, we are using GSM at some portions of the world. So then it was also voice, but this time SMS was introduced, and also there was a shift from analog to digital, from 1G to 2G. And roaming was partially okay with GSM. It was a European standard. Then when we came to 2000s, it was 3G. Then in 3G data was introduced, and it was the first generation with global standards. So global standards, I mean 3GPP. It was the first standard generation with 3GPP actually. As I said, it is the main theme for 1G it was voice, the main theme for 2G it was SMS and becoming digital. And when we moved to 3G, it was data. It was data oriented. Only 2010s it was like we met with broadband communication and app industry was born, because we were able to use broadband internet with our mobile phones, mobile handset. That's why app industry was born. Then it became everything, all IP. Then starting from 2020, there is 5G, and if in 5G it is there is always an improvement from one generation to another in terms of key performance indicators like data rate, mobility, reliability, etc. But when it comes to 5G, we started to talk about not like performance metric, but verticals. Actually, foundation of the verticals is also performance metrics. That's true. But verticals became an important topic, like remote surgery, smart agriculture, smart cities, etc. So like IoT, millimeter wave, vehicular to everything, vehicular to infrastructure, everything. We have seen it in 5G. So starting from 2030s, we will see 6G, but we don't know how it is going to be yet. how it is going to look like. So this is going to be the 6G official logo, recently introduced in April 2024. So then these two charts are from ITU, International Telecommunication Union. I'm sure you have seen it a lot so far. So then it was published in June 2024. So it is actually quite recent. So this is kind of the shape of how 6G would look like. So as you see, like this triangle over here, it was 5G. Like we had, as a user scenario, we had enhanced mobile broadband, we had massive machine type communication, URLLC, etc., etc. We had this triangle for 5G. But when we come to 6G, it becomes a hexagonal rather than a triangle. But in this triangle, we have improvements. As you see, we have improvements, but also we have some new stuff for 6G. One of them is ubiquitous connectivity, which is going to be the fundamental concept for today's seminar as well. And also we have integrated sensing and communications, and AI will be playing an important role. So sustainability, as you see over here, is going. It has been for the first time mentioned in one generation. It was mentioned in 6G. So then these are design principles, these four things: sustainability, connecting the unconnected, security, privacy, resilience, and ubiquitous intelligence. These are four design principles of 6G networks. So from today's discussion, we see sustainability, we see connecting the unconnected, we see ubiquitous connectivity. By the way, on the right-hand side, we see capabilities of 6G. In ITU's terminology, it is IMT 2030, 6G. So in capabilities, the lower half is the improvements from the legacy networks, but the upper half are the new metrics, new capabilities introduced with 6G networks. One of them is the coverage, which is related to today's discussion, NTN, non-terrestrial network, and also sustainability. It is highly correlated to today's topic. Interoperability, like we have like dual mode, our mobile handsets are dual mode at the moment, like Wi-Fi and mobile, like cellular communication, but in future we expect them to be three mode, including the satellite communication or NTN communications in general. We have also connection density related to today's topic because it is kind of main motivation behind non-terrestrial networks. At the same time, area traffic capacity. And also resilience, when we have like disaster, for example, when the network is down, we want mobile communication network to be resilient. So with terrestrial network only, it is very hard to meet this criteria, but when we have NTN in place, so resilience can be provided more easily. So these black ones are like indirectly related topics to today's discussion, like peak data rate, because or user experience data rate. With NTN, we can increase these things: peak data rate and user experience data rate. These are not the main topics, but we can also do this. Actually, we can do all of them with NTN. And also sensing related capabilities, we can also do them because like when it comes to HAPS or satellite communication, they are very suitable for IoT communications as well, for narrowband communications. Ubiquitous intelligence, how it is related? Ubiquitous intelligence means that intelligence is at every portion of the world. So then we are talking about artificial intelligence, machine learning, but when we have HAPS in place, HAPS is not only a platform that carries mobile base stations. It is also a platform that carries computing devices. Right? So then we can run our algorithms. We can have computing devices, computation softwares, resources at HAPS. So then we can have our AI algorithms plugged into the HAPS platform. So then it can be provided to everywhere, basically. So integrated AI and communication, it is another hot topic. Again, with these features, with these capabilities, computing capabilities, AI and communication can be done from one place, which is HAPS in this case. And also integrated sensing and communication is also related to this spectral efficiency, etc. As I said, we can do basically everything with NTN. We can improve, we can help to terrestrial network with NTN, but there are some like red ones need like really need NTN to be reality, the red ones. So this was the storyline. We were talking about 6G communication from 2030s. So it becomes NTN and AI. These are two main keywords from 6G. Yes, we can talk about different things like sustainability. As I said, it has been mentioned for the first time in one generation, but these are the keywords, NTN and AI for 6G communication. It means that we need to invest in these areas more and more. So, okay, what we mean by non-terrestrial networks when we talk about NTN, what we mean by that? Actually, we have three different components. There could be different portions, like more components than these, but mainly we are talking about three different components. One of them is the uncrewed aerial vehicles, UAVs. They are operating at 200 meters, and basically they are used for many things, not for communication, but from the telecommunication perspective, we can deploy small base stations on top of them, and when there is a need for pop-up networking, when there is a, for example, disaster or unexpected events or unregular events, I would say, musical concert, football matches, for example, we can just deploy them in a pop-up style. We can deploy them when it is needed, and we can just call them off when there is no need. So then they are very agile and dynamic, I would say. So then they are very beneficial to mobile communication network. But there is one problem, which is the battery. So they are usually battery operated. So then their batteries, at their flight time, service time are not that much. We are talking about minutes, like tens of minutes, 10 minutes, 20 minutes, 30 minutes, one hour at max. So this limits their service time. So then we need to take extra cautions to make them seamless. We need to have multiple UAVs. We need to optimize their charging stations, charging schedules, etc., etc. We need to optimize many things. That's why you can see millions of papers in the literature about UAV-based communication, because there are a lot to do. But even if you do them, so your service duration, your service capabilities are still limited. Then we have HAPS, high altitude platform stations. They are operating at stratosphere, 20 kilometers above the Earth surface. I'm not going to go in detail in this slide because I will be talking about that a lot. Then we have communication satellites. There are three types, as you know. There are low Earth orbit ones. So altitudes are up to 2,000 kilometers, but nominal, on average, I would say like 500 kilometers. Starlink, for example, is operating at 500 kilometers altitude, and they are usually used for telecommunication and broadband services. Because they are closer to the Earth, they can be used for broadband services. Our path loss is not that affected. That's why we can use them for telecommunication and broadband services. Then we have MEO, medium Earth orbit satellites. The altitudes are starting from where low Earth orbit satellites ends, 2,000 kilometers to 35, 36 kilometers from the Earth surface. They are mainly used for navigations like GPS. Then we have GEOs, like Turksat 6A recently launched. It was a GEO satellite. So then, as you see, for low orbit satellite and medium orbit satellites, we are talking about ranges, like from this point to this point, from this point to this point. But when it comes to GEO satellites, we have a specific, precise location as an altitude, right? The reason is that they need to be static, like their projection on Earth needs to be static. So that's why they need to orbit with the Earth movement. So that's why their placement in in terms of altitude is that precise and fixed. They are mainly used for TV broadcasting and maritime communications. So today we will be talking about HAPS. A quick comparison. So UAVs, as I said, they have limited flight time, but satellite has a very long service duration, basically. Like we are talking about years here. Here we are talking about we are talking about minutes, but we are talking about years when it comes to satellite. So as you see, there is a gap between the two. This is a very long service duration. This is a very small service duration. But HAPS is just in between. We are talking about 1 year, for example, 1 year time frame. So it is just in between of these two things. So this is red one is the main bottleneck. So we cannot talk about this very long service duration as bottleneck. It's a favorable thing, but limited flight time is a problem. So then HAPS is solving this problem basically. So when it comes to latency for UAVs, because they are operating around 200 meters on 120 meters, the latency is almost same with, not almost exactly same with the terrestrial networks. So then we don't talk about latency for UAVs. But when it comes to satellites, especially for GEO or MEO, we really talk about latency. Even for LEO, right? Round trip delay is a lot higher than terrestrial networks when it comes to LEO satellites. So then who solves this? Again, it is HAPS. HAPS has reasonable latency because it's 220 kilometers from above from the Earth surface. So it is just in between. So this is 100 meters. This is at least 500 kilometers. So this is again in between, which is 20 kilometers of altitude they have. So in terms of footprint, this guy is a very low footprint because again it is from the geometry, it is 100 meters above from the Earth. So then the footprint becomes very, very, very limited. But when it comes to satellite, because they are very high from the Earth surface, the footprint is enormous. Again, there is a problem here, limitation. Again, HAPS solves this limitation. As you see, each technology like UAV and satellite, each has good positive attributes on some points, but negative attributes at another point. But HAPS is just provide something in between. It's a really good solution. That's why we can call it as a technology that can fill in the gaps between the technologies in non-terrestrial networks. So it is a technology of stratosphere. I call it an uncharted territory, but it is not uncharted territory. Compared to UAVs and satellites, I have named it this way, uncharted territory, but actually it is not. It is a well-studied concept, basically. Why we are using this? Why we are using the stratosphere for HAPS communication? Why not like 30 kilometers or 40 kilometers away above the Earth surface? Actually, there are really good reasons for this. First one is that it is above the clouds, so that the solar panels can continuously capture the energy from the sun. So there is no block between the sun beams and the HAPS surface. So it is, I would say, there is more line of sight between sun and HAPS in this regard. And also the wind is relatively lower. So as you see at around 20 kilometers, so then the wind speed is like there is a local minimum around that. So then when you increase it a little bit, when you increase it a little bit, so as you see, the wind speed is increasing a lot. Why this matters? It matters because HAPS systems should be quasi-stationary. It means kind of stationary, right? They need to be stationary at their point. But the thing is that when there is a wind, so then there is going to be a jitter, right? So then they will be moving back and forth. So this movement is okay, but and if the wind is very strong, so then the wind can move them more than actually expected level. So in order to avoid that, they use their energy sources to avoid this, right? They use some propulsion systems, for example, to avoid these kind of things. So then when the wind speed is lower, so they use lower energy from their onboard energy systems or from the renewable energy sources. So there's no air traffic because airplanes are flying at 10 kilometers. So this is 20 kilometers. So there's no air traffic. It is not affected from that. And also large footprint compared to terrestrial and UAVs, which is good. And also smaller footprint compared to satellites, which is also good. Both of them is good because large footprint is good to serve many users. But at the same time, if the footprint is very large, so then there becomes a problem, right? So for example, so it means that you are serving many users separated hundreds of kilometers away from each other from the same point, basically same resources. So then it means that you need to reuse this resource. Normally in terrestrial networks, there is a concept of frequency reuse, right? So then you can spatially distribute the users. So then you can reuse the same frequencies at different locations in the region. But these locations are separated 100 meters away, or 1 kilometer away. They cannot affect each other. But this time, you are talking about hundreds of kilometers away, users from hundreds of kilometers away, but they can affect each other in terms of interference. And also, there's a concept of pilot contamination, right? So then this is a reality when it comes to NTN because they are serving in very large distance. So large footprint is a plus, and also small footprint, it's also plus when it comes to NTN networks. Again, they are closer to the Earth's surface, so then they can incur less latency. So what is HAPS? So there's the ITU, International Telecommunication Union's definition about that is the radio station located on an object at an altitude of 20 to 50 kilometers and at a specified and fixed point relative to the Earth. So this is important. There's given a range is given from 20 to 50 kilometers, but actually we are using it around 20 kilometers for the reasons that I just mentioned, in terms of wind, basically. It is also called near space because near space or stratospheric communication, near space communication, there are different terminologies in this. And they do not orbit, it means that they are fixed. They are called quasi-stationary. When you deploy it on top of, for example, this region, Gebze, so then they should stay over there to serve the people around this region. Why this not orbiting is important? Because for LEO satellites, they are orbiting, they are moving very fast. So then when they are moving very fast, there becomes other problems like networking problems, handover problems, etc., etc. We don't have those problems with the HAPS. What kind of HAPS we can have? Like free floating balloons, we can have airships, powered fixed wing aircraft. There are different types available in the market at the moment. So they are usually using solar power, and they also have batteries, onboard energy sources. Mainly, we have two different types of HAPS. One of them is lighter than air, or we call them aerostatic HAPS. There's a company, Aerostar. They are building this kind of HAPS aircraft, like lighter than air ones. So then they are usually balloons like this. So this company, Aerostar, is building this kind of HAPS. They are actually floating in the air, right? They are floating in the air. And the balloon ones are usually unpowered, but sometimes they can use solar power. So there was a project from Google. It was Google Loon. It was terminated because it was not successful because due to some business cases. But it was a balloon one, and it was using the wind directions to move around, right? So then it was using some data from national institutions about the weather conditions, wind speed, wind directions, etc. So then when it wants to go from point A to point B, it was like, for example, it wants to go from point A to point B in this direction. So it was checking the data in terms of the wind. Then it was going to portion of the air that where the wind is going in that direction. So then it was going there, like for example, above the wind is going to the right direction, so it was going there. So then the wind can move it towards point B. So it was using this kind of technology. And also for airships, they are mostly powered and they are using some propulsion systems as well. And also we have heavier than air HAPS. We also call them aerodynamic HAPS or heavier than air HAPS. So the most famous one is the Airbus Zephyr. They are using the electric motors and propellers as well. But because of their shape and their capacities, they can carry less payload. Their capacities are less, and they need to move forward and circle around to keep their positions. For these two, according to the needs of the application, if you want the HAPS to stay there for a longer time, like for years, you would choose these lighter than air aerostatic HAPS solutions. But if you need kind of pop-up services, for example, there is a wildfire or there is a disaster like earthquake we had 2 years ago. So if there is something like that, so you might need this aerodynamic HAPS because you can easily deploy them to the point, but their capacities or capabilities are limited compared to lighter than air HAPS systems. So then, so as I said, Aerostar is building, manufacturing this type of HAPS. It's one of the main companies in the world. There, as you see there used to be some tethered HAPS as well, but now it is not allowed until 2 kilometers above from the Earth's surface. I guess they are allowed, but above than that is not allowed with tethered one due to some safety issues. So then this Aerostar HAPS, lighter than Air 1. So then this is heavier than Air 1, Zephyr HAPS built by Airbus basically. So we are envisioning this kind of system. So then there are satellites, NTN satellites, then HAPS, they're working together, collaborating. At the same time, it is not available in this picture, but there will be some UAVs as well. So then there will be multi-level or multi-tier, I would call, networking. So then from terrestrial, UAVs, HAPS, and satellites. So with that, there can be different applications. For example, you can use them for wildfires, so to pinpoint the wildfire. So this is one of the important issues when you are fighting against wildfire, right? Precisely where is the fire, right? So to pinpoint that, you can use this NTN components for maritime communications or rural communication. So harder to reach areas, I would say. So for maritime communication, it is not possible to deploy terrestrial networks. Right? So you need NTN components there. And also there are different usages for smart agriculture or like, for example, jungles like this when you need IoT connectivity. So it is harder to reach area as well. And also the demand is limited. So it is not profitable to deploy new base stations, new towers to those kind of regions. So that in those regions, you can use these NTN systems. What are the use cases? As I said, HAPS is an IMT base station. This is the ITU terminology. ITU doesn't call it HAPS or HAPS base station. ITU call it as HIPS. HAPS is an IMT base station. It means that HAPS will be using legacy, like it is going to be harmonized within the mobile communication network, cellular communication networks. IMT base station means that like cellular communication, cellular communications. So the HAPS will be carrying base stations. HAPS will be carrying cellular base stations basically. So that this is the main thing we are deploying. For example, LTE or 5G or 6G base stations on top of HAPS. Then we can provide service extra capacity to the required regions. And also sensing and communication is another thing. Sensing and communication, they can be disjoint things, but at the same time jointly. We can do that. It is called integrated sensing and communication, ISAC, or joint sensing and communication, JSAC. You can do them together or separately. So then there can be a HAPS with certain frequencies, like not related to this IMP base station thing. So you can use separate frequency bands for sensing, other frequency bands for communication. This is one approach. Another approach, you use the same frequency bands for both of them at the same time. You can use them for localization, positioning, navigation, etc. And also, again, for wildfires, pinpointing the fires, you can use them. Intelligent transportation systems. When, for example, like you are using intelligent transportation, vehicular communication, then your car is smart, the other car is smart, but in the region that you are in, there is no wireless connectivity. At that time, HAPS can be a solution because, as you know, terrestrial networking is not available everywhere. Reconfigurable intelligent surfaces, they are hot topic like HAPS. They are also hot topics, so they can be used together. So then you can deploy RIS as a relay to on top of HAPS, but there are a lot of challenges. In theory, yes, it is true, but in reality, practically, it is not that easy thing. And computing and caching, as I said, you can deploy some computing capabilities on top of HAPS. So there is another good thing about the stratosphere. The temperature is very low. So then the main problem with data centers is cooling. So then, because it is very low, the temperature is very low in stratosphere, so then you don't need to worry about that, right? You don't need to take extra caution for cooling because it is a natural cooling over there. Earth observation, as I said, another application. Border control, another application, because it is not that easy thing for longer borders. So now it comes to, I can skip this part very quickly, a little bit boring stuff, as I said, propagation modeling. So then how we can calculate the propagation for HAPS, because many things are okay for similar to terrestrial networks, but because it is 20 kilometers above from the Earth surface, we need to rethink some concepts, fundamental concepts like path loss. The fundamental path loss would be the same, but when it comes to overall propagation modeling, there are other things that we need to consider compared to terrestrial network. For example, so this is the simplified methodology recommended by 3GPP as well. So then how we can calculate the propagation or propagation model of path loss from HAPS to ground user. So as you see, we need to calculate the loss probability because you see it says, sorry, you see it says assign propagation condition and loss or loss. So it's a binary. There's a binary system in 3GPP calculations. So if it is n loss or loss, if it is loss, things change a little bit. If it is n loss, like loss line of sight, n loss non line of sight, you need to determine if you have loss or n loss, if you have a direct link with the user or not. You need to determine this first. So then there are some statistical things that you can use. For example, this thing, these are some empirical results. Based on your elevation angle, what is your probability of having line of sight? So based on the scenario as well. If it is dense urban scenario with 10 degree of elevation angle, so this is around 28%, you can have like line of sight. But as you see, the same for the same elevation angle, it is almost 80% for suburban or rural scenarios. So then for this, as you see, when you increase your elevation angle, so then your chances to have to catch the line of sight increases. And also it is almost for certain you can have loss for if your elevation angle is very high. So if you are in rural region, that you are almost certain that you can have a loss connection between HAPS and ground users. So then path loss is calculated in this way. So this is the main calculations. So then this is the path loss, the total path loss in dB that we can calculate. So when you, as you see, there are 4 different components. So this PLB is the basic, we call it basic path loss. So it is the path loss that we use in terrestrial networks, basic path loss, like free space path loss plus shadowing plus clutter loss, etc., etc. Very basic one that we can use. So most of the time, with just this one, we are okay in the terrestrial networks. But as you see, there are 3 more components when it comes to NTN. So attenuation due to atmospheric gases, because at certain portions of the air or space, so there are different gases like accumulated around, right? So for that reason, and they have different absorption features. So you need to take that into account as well, so that it is included in the path loss, overall path loss. Then also scintillation is another concept when it comes to scintillation is another concept. This is either ionospheric or tropospheric. You can have 2 different scintillations. This thing we usually don't have in terrestrial networks. And also building entry loss. I can say that this could be included in the terrestrial network as well, but these 2 things are specific to non-terrestrial networks or HAPS. Okay, the basic path loss is PLB. How can we calculate it? It is based on this free space path loss, basically. This free space path loss, it is based on this when your carrier frequency is gigahertz and your distance. It is a function of carrier frequency and distance. When it is the log 10 of carrier frequency and log 10 of distance, and also we have a correction constant here. This is calculated based on these units. It is unit correction because we are using gigahertz here and a kilometer as a unit for distance. We need to add these things. So when I change these units, like when I make this megahertz, when I make this meter, for example, then I need to change this to some other things. For example, when I make this megahertz, I'm keeping this kilometer, so it is going to be 10 to 6 rather than 10 to 9. So it is going to be 30 dB less than this one. Okay, this was the basic one. So then this calculation is also a little bit different than the terrestrial ones because we need to take into account the Earth's curvature as well. So as you see, there's another, like normally with Euclidean calculations in terrestrial network, we are good to go. But for NTN calculations, especially when it is very high, for UAVs, we don't use this equation. But for NTN and satellite, we have to use this one. Does it change a lot? It is not significantly changing. But if we need some precise location, so then we would need to include this equation for distance. Another thing is that like we need to add, like this was the free space we calculated, then we need to add some shadowing fading on top of that and clutter fading. So then these are different empirical results included in 3GPP documents. So based on your scenario, dense urban, sub-rural, and rural, so how much like SF shadowing fading you can have, or clutter fading, clutter loss you can have. There is a table for it. Is kind of a lookup table. You can use this for that. Then there are some other stuff, building entry loss. So then depending on the frequency and material used for building, you need to take this into account as well if you are talking about indoor users. If you are talking about the outdoor user, we can just ignore this. And also scintillation, if it is above 6 gigahertz, we have ionospheric scintillation, or below that ionospheric scintillation, above that we have tropospheric scintillation. We need to take these, like there are different calculations with these. So then this is a bit boring. So then as you see, things get dirty when we go deeper. That's why I guess it is, there is a, I got the alarm from here. I'm just stopping the, this kind of mathematical derivations with this slide. Okay, it is not a feature anymore. Like we were discussing that, okay, in future we would have these kind of things, but now it is not a feature, it is happening right now. Because like Eurostar, again, I'm not promoting this company. I'm talking about a lot about this company, but I'm not promoting them because there are only few companies working on HAPS. That's why there is a lot of iterations of it, Aerostar. So then in April 25th, so then there was a news. They were in stratosphere for 500 days. So almost 2 years, they can stay in the stratosphere. So then compared to UAVs, it is a lot. We are talking about minutes, tens of minutes in UAVs, but with HAPS, we are talking about years, 1 year or 2 years. So then in terms of cost of operation, yes, compared to UAV is very cost effective, very cheap. This is like much more expensive than UAVs, but you see, you can use them for a longer time. Another thing is that I followed this in last summer there were like, as you followed from the news, wildfires in the US. So then high altitude balloons actually were used to pinpoint the wildfires in the US. So then this was another thing. So they are being used. This is the main message. Another thing is that there are different trials. SoftBank is making a trial, and also they are successful. These are successful trials. They tried some communication HAPS systems, and it was quite a success. Another thing, so then there are different agreements between the institutions or companies related to this HAPS, because there's a potential. They have started to invest in this. And also, maybe you know this Flight Radar 24. We can follow these planes on this website. So then they have included HAPS as well. If you go there, you can see HAPS here, for example, around somewhere Dominican Republic, around some during that wildfires in the US, I was following the wildfire on this website as well. There were a lot of HAPS systems around the region in the US as well. Now I could catch only a couple of them, but at that time. So as I said, when there is a need, they can be deployed in a pop-up manner. But for other, like again, this was manufactured by Aerostar company. Okay, more recently what happened? So then World Economic Forum, so then they just released a report talking about top 10 emerging technologies of 2024. So as you see, HAPS is one of them, one of the top 10 technologies, emerging technologies of 2024. This was also important. It was attracting attentions not only from academia but also industry. That's why they had started to do these kind of agreements and trials, etc., etc. So then the HAPS market is growing a lot. So as you see, like 10%, around 10% grow over the next decade, and the market value today is around 700 or 800 millions. But there will be a potential of annually 10% grow from now on. And there's a lot of potential in terms of business as well. So in this report, it says HAPS technology is now economically viable for commercial and real-world deployment. So far, we were talking about the potentials, but from now on, we talk about how it can be used in real life. And we are not how it can be used; they are being used actually, as of today. So there is another thing, World Radio Conference 2023. It is not that recent, but it is not that far. So then it was December 2023. So what happened is that, so as I said, ITU uses this terminology, HIPS terminology for HAPS. So it happened between November 20 and December 15, 2023 in Dubai. It was like one month event. So they said, okay, HAPS is for rural, remote, and disaster management for 5G. So then they considered HAPS for rural, remote, and disaster management. But what about 5G and beyond, 6G and beyond? So then we envision that, okay, it can be just for rural, remote, and disaster for 5G. It means that we can use it from now. But for 6G and beyond, it will be for ultra-dense networks as well. Just on top of the main cities, it is very likely that we would have HAPS systems. So what happened in this conference, WRC 23? Previously from WRC 19, if I'm not wrong. So it was this 2 gigahertz frequency band was allocated for HAPS or HIPS communications in IT terminology. It was fixed, you just had this one. But now from WRC 23, so then we now have 4 different frequency bands. It means that things are getting more favorable for HAPS communications. Industry is investing, research institutions are investing, and also like you see global agencies like IT, they're also making favorable decisions with regards to HAPS-based communications, aka HIPS. Now we talk about harmonized communication. It means that HAPS is not like when it comes to LEO satellites or satellite communication, we talk about different frequency bands, right? Out of band communication. Terrestrial communication is something, satellite communication is another thing. Even for on-device communication or direct-to-device communication, we talk about different transceivers, designing different transceivers for satellite communication and plugging them into mobile phone, in addition to the terrestrial network. So then there will be a trial mode when it comes to LEO. But when it comes to HAPS, it is not, the story is not like that. The story is that your unmodified phone, it means that your mobile handset, you are using it now, you can use it for HAPS communication as well, because like 4G, 5G, 6G base stations will be deployed on top of HAPS. When it comes to satellite, it is another story, but HAPS has the story of terrestrial communication. So this is another plus for HAPS compared to satellite communication. What about the hot topics in HAPS-based communication? One of them is that RIS deployment. How can we deploy RIS on top of HAPS? And also can we use this? So the idea here is this. So for example, at some portion around here, for example, at night, this region is not used that much as I would imagine. So then there are some base stations around. They're underutilized at some times of the day. But somewhere in a village around here, like 100 kilometers away from here, there's a village, but there is no mobile connectivity. One solution is that you can just deploy a base station there. This is one solution, but from mobile network operator perspective, this is not cost effective, right? This is not profitable. They would not do that because there are like only 50 people living there. For 50 people, they would not make this investment. But the idea is that if you deploy RAS, reconfigurable intelligent surfaces on top of or underneath the HAPS, so the frequencies that you use at these base stations, underutilized base stations, it can be relayed to those people in that village. Yes, it is pretty much opportunistic. It is very good. In theory, on paper, it is very good, but in reality, it is not easy to realize. But yes, if this is the vision, so then we will need to deal with the challenges one by one, so then to achieve this. This is the vision, basically. Another thing is that, as you remember from the beginning of this presentation, sustainability, what I told you that sustainability has been mentioned for the first time in one generation, in the description of one generation, which is 6G. So sustainability will be a hot topic in 6G and beyond communications. So we need to design our networks in a sustainable manner. But the thing is that, can we use HAPS for sustainability? So I'm actually doing a lot of research in this, like HAPS-based cell switching is the main, precisely what I'm doing. So then HAPS-based cell switching, I will show some results about that as well. So we need to design our HAPS communications in a sustainable manner. Is another hot topic in HAPS-based communication. And also multi-tier network architecture. It needs to include terrestrial networks, UAVs, HAPS, satellite, all of them integrated. So again, on paper, on this slide, it looks very good, visionary, but the thing is that if you integrate all of these things, it is not something that you can do overnight. You need to invest that a lot. So, but it is also important if you can integrate everything. It means that you can have seamless connection anywhere in the world, even if you are in the ocean, just in the middle of the ocean, or like in Manhattan, New York. It doesn't matter. You can have that connectivity if we achieve this concept. Another thing which is very hot topic these days, as I said, integrated sensing and communications. Can we use it with NTN or specifically HAPS? Another thing. So generative AI, you know, it is another hot topic these days. AI has been a hot topic, but these days it is generative AI. Can it be used for HAPS? We have a study, I will show it very shortly. To use it with like HAPS, generative AI at the same time, how can we take the benefit of generative AI when it comes to HAPS-based communication? So this one study that I have been doing, multi-layer network formation through HAPS base station and transmissive risk-equipped UAVs. So that in this work, what we did, so then this is the network architecture that we are proposing. So then there is HAPS on the top layer. So this HAPS is providing wireless connectivity, but there is also a UAV. UAV is, as you see, that carrying IRS or RIS component. So the connection coming from here, the signaling coming from here, is relayed to the ground users by using this UAV RIS. It is not RIS, it is T-RIS, it is transmissive RIS. It means that it is not two-dimensional. In like traditional RIS equipments, it is reflective. So then there is an incident wave, and it is just reflected through this RIS. But for this transmissive RIS, in this setup, it is more suitable because the electromagnetic wave coming from here can be transferred from this RIS to this. But if we had a conventional RIS, we couldn't use it in this setup, right? So because it is reflective, so then if you have any connection from here, right, so that it can be reflected towards that RIS. This is okay. But when you have a connection from here, how could you reflect this to the ground user? It is not possible. So that's why we use very new concept called transmissive RIS or T-RIS. So then there are different things. So then we just measured how we can, like performance evaluate. We did performance evaluations in terms of energy efficiency or sum rate, how we can improve the sum rate of the users, what happened to energy efficiency of the network sector, etc. Because as I said, sustainability will be quite an important topic. So we use IoT devices as users here. So this is the story that I told. So then we use NOMA technology as multiple access and MISO for the antenna technology for this setup. So this is the work that we have. It has been submitted to IEEE WCNC. So another one. So this has been recently published on IEEE Transactions of Vehicular Technology. So in this setup, we have one HAPS. So then there are terrestrial base stations, but we are opportunistically switching them off and offloading the traffic to HAPS. Also, okay, this seems trivial, but actually it is non-trivial because there will be a lot of small base stations. Like we talk about hundreds of base stations in a small area. So which one to switch off, which one to keep active? So this is the optimization problem. And the ones that we are switching off, their traffic needs to be offloaded to HAPS. Traditionally, we had been doing this with terrestrial macro base stations. We had control data separated architecture. We were using that. When we switch off one small base stations, its traffic is transferred to the terrestrial macro base station. So then we redefined the problem. What if we don't have a macro base station, or what if on top of a macro base station we have HAPS on top and just offload the traffic of switched off base station? What would happen? And also there is another problem here. So it's been almost 1 hour. I don't want to take too much time. So there is another problem, which is cell load estimation problem. This has been introduced for the first time in the literature. The problem was that we had been doing this cell switching technology, cell switching algorithms. There had been very advanced algorithms in the literature. If you just look up for cell switching for mobile communication, you would see very sophisticated algorithms. But there was one problem. So these algorithms were assuming that the traffic of base stations are known. It means that, okay, in this time slot, I take the decision of switching off particular base station, for example, this guy over here. When I switch that off for the next time slot, how can I know it's traffic? It is already off, it is sleeping. How can I know it's traffic? But in literature, we assume that we know it's traffic as if it was awake. But in reality, how come? So then this was the problem. It means that in the literature, the decisions are taken with the assumptions that we have zero estimation error, kind of. We were not saying that, but we were saying that we have perfect knowledge, but in reality, it was done by the assumption that there is zero estimation error, which is not possible. Actually, we introduced this problem and we implemented different reinforcement learning algorithms for this, and the results were very good. So as I said, these were published in I took the Transactions of Vehicular Technology. So we also proposed lightweight Q-learning or full-scale Q-learning. In full-scale Q-learning, it was the computational complexity was 2 to n, which is challenging for large-scale networks. But we said, okay, this works very fine, like this full-scale one. I'm not showing the details, but this full-scale one is working very fine. Okay, that's very well, that's fine. But the problem is that when the network size grows, when you have, for example, 100 small base stations, number of possibilities is 2 to 100, which is infinity. So then you cannot solve this problem. So then we introduced lightweight Q-learning. Also, it was giving good results. So when we talk about sustainability, it is an important topic these days. As I said, not because ITU mandates us that sustainability is important. Because of the environment, it is important, right? So then we need to take an action now. When we talk about sustainability, there are 3 different sustainabilities: economic, environmental, and social sustainability. The sustainability that I'm talking to is environmental sustainability. But when you have that, so then automatically you provide economic sustainability as well, because when you reduce the amount of energy consumption by the mobile base stations, it is also reduction of energy bills for those mobile network operators, and it is a kind of a business sustainability, and it is an implications on social side as well. So why energy consumption is increasing? Network densification, because there is more demand, more YouTube videos, more online gaming, metaverse, etc., very sophisticated algorithms. That's fine, but to be able to do that, we keep deploying base stations. We call it network densification. So then our network energy consumption is kind of multiplied. Also, power consumption of a single base station is also a lot. Like 50 to 60% of radio access network comes from the base stations. So this is also a lot. So this is a lot, and also for this a lot of things. So then you deploy a lot. So it means that a lot. So that in the end, so then the energy consumption soars a lot. So then emerging applications, online video broadcasting, AR, VR applications, online video streaming, etc. There are a lot of things. So these things requires you to, like you, me, and everyone to use these technologies, like watching YouTube videos, Twitch videos, whatever it is, online gaming. So because of that, like we demand this. Because of this demand, mobile network operators deploy more base stations, network densifications, and these base stations consume a lot of power. That's why we have this problem. So the problem, the work that I just mentioned is cell switching. It's a solution that we are proposing, not us. It has been proposed in the literature. So this picture I've taken, it says this door must remain closed when not in use. The same principle. the base stations that are not in use should be switched off. We shouldn't keep them active. So this is the same analogy here. Base stations that are lightly used or not used at all are put into a sleep mode. So then why we need HAPS? Because our studies have shown that capacity is everything in cell switching. Because when you have more capacity, you can offload more traffic. If you can offload more traffic, it means that you can deploy more base stations. Sorry. Yes. United Nations Sustainability Goals, Sustainable Development Goals. So with these works, we can provide many of them. We can satisfy many of them. These are just some examples. Climate action is one of them. So another one, I'm going to keep it short. So this is, we just submitted. This is the cell switching. Okay, we are talking about multi-tier network formation, but why not using this multi-tier network formation for cell switching operations? Why we are just limited to terrestrial, or why we are just limited to HAPS? Why not we have all of them, right? Tier 1, Tier 2, Tier 3, Tier 4. Tier 4, and there are different portions of these Tier 4. Why we are not, if the capacity is everything for cell switching operations, why we are not using or utilizing all of them, right? So this is the idea, but there's the problem is that latency becomes a problem here. If you are running a latency intolerant applications on the ground here, so you would not like to be offloaded to a LEO satellite, for example. So then when I do the optimization, I need to take this into consideration as well. So here AI is my key tool to solve these problems for sure. So we have seen that, as you see, when user density increases, gain increases as well. But when you deploy more, like for example, this is only terrestrial, right? This is only terrestrial network. As you see, after some threshold, there is no gain when you increase the user density because the capacity is already exhausted. But when you deploy more tiers, like for example, when you use HAPS, you see there is more gain, and gain exhausts at a later point. But it exhausts. But when you keep deploying like different tiers like this, tier 1, tier 2, tier 3, your gain would be a lot higher than what you could get from the terrestrial base stations. This is another work we just submitted. Again, we take the advantage of HAPS for disaster scenario. So what would happen in, can we use NTN networks for disaster scenario? Our solution was using tier 2 or UAV communications for RAN access, radio access network access, like from users to the network. For this access, you can use UAV base stations. But for backhauling, these UAVs needs backhauling. There could be a HAPS on top. So then for the backhauling, you see there could be another link between base stations, UAV base stations and HAPS. Another multi-layer NTN network formation, but this time we are using it for disaster scenario where many portions of the network, terrestrial network is down. The idea here is that we cluster the users on the ground, which is very common practice for these kind of things. You are clustering the users. Because it makes sense, because in these kind of things there are some centers like hospitals, etc., where people accumulate. So then you can use them, those places as hot points. So then you can cluster people. So then, as you see, there is a cluster of people over here. So then we used K-means clustering, or one machine learning algorithm, to cluster these people. And in the middle of each cluster, we are deploying a UAV base station. This is very traditional method of doing this. But so, as I said, what could be the backhaul? For the backhaul, this time we use another clustering for these base stations, for these UAV base stations. Then we find the centroid point. So, for example, centroid point is found somewhere around here. So then we are looking for the closest UAV base station to that point, which is this guy. We attract, or we assign this guy, this base station, as the head of this. So then we run an ad hoc networking over in this network of UAV base stations. And also only this guy, communicate with the HAPS base stations in order to prolong the lifetime of or the service time of this NTN network, which is critical for search and rescue teams, for people affected, for people who are trying to reach their loved ones. Okay, this is the last one, as I told. So then here we talk about strategic demand planning in wireless networks. Can we use generative AI to save spectrum and energy? So the idea is that, okay, the generative AI has been a hot topic. It has a lot of capabilities. So then why not we use this in favor of wireless communication networks, generative AI? So the thing is that in our studies, what we are saying that, okay, improve or enhance the network capacity. This is one thing. Or how can we enhance the network capacity? How can we deploy more base stations, etc., etc. All the solutions are from network side. But what we said is from looking at the picture from the other way around. How can we reduce the traffic? Not improving the capacity, but how can we reduce the traffic? So because this could be an important topic in disaster scenario in the previous slide. So network, we cannot enhance the traffic, network conditions, right? So then in first 3 days, it is not possible. In 2 days, it is not possible. We cannot improve the network capacity, but can we reduce the capacity, demand? So then this is the demand planning. This brings the demand planning. So first, we label the demand. What kind of user demand is it? It is a critical one or non-critical one. Critical one, for example, search and rescue teams. Their data should be critical because they need to reach each other for emergency keys, etc. Their data could be or a person who is under the ruin, his or her data would be critical. But for me, sending a WhatsApp message to my friend for irrelevant stuff, it is non-critical data. First, we need to classify this. Once this is classified, it means that we can schedule this, right? For example, this guy for critical, straightforward, like we need to send it, we need to transmit it. There's nothing to do because it is important. It can cost a life, right? This is important. But for non-critical one, we can schedule it when the network conditions are more better. So then we can transmit that data. So I'm sending my selfie photo to my friend. It is not that critical, not that important. So then it can be transmitted in 2 hours, right? So in that critical condition, I'm not talking about regular operations, but in that critical conditions, it doesn't change anything that if my selfie photo is transmitted to my friend after 2 hours, it doesn't change anything. So it can be done. At the same time, if we can convert the data. For example, if I am sending a video, can we convert it to a text? Because we know that generative AI tools like ChatGPT, other Gemini, Google Gemini, etc., they can do that. They can convert the data from, for example, video to text, photo to text, etc., etc. Can we do that? Can we convert this, or can we compress the data? So that if we can do this, we can do many things. So then there are different use cases. We discuss sustainability, again, cell switching. Can we use it for cell switching? For disaster scenario, can we use it? For different things like interference management, user association, we discussed all these things. And in almost all of them, we have, not almost all of them, in all of them we have HAPS or HIPS as a main component of the network. So this is the convergence of generative AI and HAPS systems. Okay, challenges. There are different challenges. 3D network formation is not that easy as I discussed. So massive MIMO or ultra massive MIMO, it is an important thing to improve the signal quality or data rate, etc. But when you deploy HAPS, so then massive MIMO or ultra massive MIMO is not that easy. Actually, it is easier on one hand because you have larger area, you can deploy more base stations, this is plus, but on the negative side, you have many problems. You have pilot contamination. The pilot signals of different users from hundreds of kilometers away can contaminate each other. And at the same time, you lose the diversity because the links are loss dominant. So then you lose the diversity. Diversity is everything for MIMO. So then you lose this. So risk integration, as I said, there is going to be a jitter. It means that the HAPS is not
that's stationary. It is quasi-stationary. It means that it is stationary somehow, but a couple of meters moved forward and back and forward. So this is somehow okay, but it creates a lot of problems in terms of optimization. When you optimize risk, weights, coefficients, for example, for one location, when HAPS moves a little bit, so then everything needs to be considered or re-optimized. So then these are other problems. Isaac, it is not also easy. Backhauling. So okay, when you talk about HAPS, it means that footprint is, we are talking about 500 kilometers of footprint. It means that millions of people. So then you are responsible for the data of these millions of people. Okay, you can provide RAN service for it, but what about the backhaul? So then just from one point, you serve those users, but your backhaul would be limited, right? So this is another problem for that. Privacy and security concerns. Most of the time for computational services, HAPS is used, but your data is not secure. And energy management, because it is like onboard energy and renewable energy sources are used. So then their scheduling and optimizations will be pretty much important. So then I'm just gonna skip this very quick. So why AI would be needed in this storyline? Because it's model free. For other optimization methods, you need the model of the environment in advance, but you can design your AI algorithms model free. It means that it can interact with the environment without any prior knowledge. So it is a plus. It's a plus. It is a requirement for wireless communication network, because you cannot know the environment precisely in advance. So learning is a plus, because for other conventional optimization algorithms, when things change a little bit, you need to rerun them from scratch. But when it comes to AI or machine learning, so then when things change a little bit, you can just update them, not changing, starting everything from scratch. Just update them. The update would be enough. So there's a lot of data. Why not to use machine learning, which is the main ingredient? Data is the main ingredient of AI or machine learning algorithms. With generative AI, we have more capabilities, and we can predict the things. So for proactive processes, I would say. Are we done yet? For sure, we are not done yet. We need to work a lot to unleash the full potential of HAPS and opportunities. We need to work very hard. We are just around here, so then we have a lot to do. Yeah, we have some future works, end-to-end integration. It is an open topic, open works, open issue, I would say. End-to-end integration, how can we do that? How can we efficiently use renewable energy sources, not just for powering these air vehicles, and also for different things like for sustainable development. Realistic HAPS emulations, this is another thing, so then we don't have them yet. Realistic, we are using some simulations, but they are not that available. Seamless generative AI applications, it is another thing that we need to think of that. So collaboration of satellite and HAPS, it can be covered in this end-to-end integration of TNN and TN. And thank you. I'm pretty much open to questions and collaboration opportunities. Any question? You need to take this.
You mentioned the backhaul problems or challenges. Do we have a summary about the state of the art for backhauling now? And what about the latency if we do the backhaul over the GEO or LEO satellites?
So there have been, actually it is a very good question, thank you. There have been works related to backhauling through satellite networks, like from using LEO network. Because when it comes to HAPS, conventional means of backhauling is not possible. You cannot this. So FSO links, it is also problematic, because
Resistive to
yes.
geometric misalignment.
Yeah, misalignment, and that they need to be precisely aligned. So as I said, because of the jitter, so then you are moving back and forth. It is not also possible. You are losing the opportunities. Fiber optic links, which has very huge bandwidth, you cannot use it. FSO, which has very large bandwidth, you cannot use. You are left with wireless, like RF components. So then you need to use satellite. So then the state of the art using the satellite things. But as you said, there becomes another problem, latency. It's a trade-off. I cannot tell you that this is the solution. It is I could write it into open challenges, actually. Thank you very much. It's a good discussion point, actually. Another question? I think we don't have any. Thank you. Thank you for your interest.